Welcome back, everyone. This is video 2.3, Hess's Law, example problem number 3. So this is our second practice problem, and we are going to be talking about rust. When we think about rust, we might not think about a chemical reaction happening, but there is a very, very slow reaction between iron and oxygen. So rust, or iron trioxide, is formed during a very slow reaction between iron and oxygen, which can be seen here. Find the molar enthalpy of formation of iron 3 oxide given the following reactions. So we have 3 different reactions down here that we are given. We're going to use these reactions to figure out the molar enthalpy of formation for rust. So just a reminder, pause it here if you want to review the steps to solving Hess's Law problems. If not, we can get right into it. So our first step here, does adding the 3 known reactions give the targeted reaction? Wow, that's big. So a lot of things in this reaction. When we add up the 3 known reactions, and if we simplify it all down, we got 2 aluminums here and 4 here, so that makes 6 together. Put our oxygens and everything else that's common together, and we're left with this equation here. And we can call our target reaction on the bottom is not this. So that didn't work. So now we know we're going to have to manipulate some or one of the known reactions. Yeah, so that did not work. So do we need all 3 given reactions? Let's examine this. In our target reaction here, we want an iron, solid iron. We can see that that's in equation 3. We have solid iron. Is it anywhere else? No, it's not. So we're going to need equation 3. So if we're going to need equation 3, that means the rest of this stuff we're going to have to use. Okay, and that's good. Here's our rust. So we have our iron and we have our rust. We have 2 extra things in this equation though. And they're not in our targeted reaction. The only thing left that we need is oxygen. So that means somehow we're going to have to get rid of these. And we can see that we have aluminum and our aluminum oxide both in equation 1, reaction 1. And it also has our oxygens. So we can see that these 2 are going to cancel with the other aluminum terms up here. And we're going to be left with our target. So we do not need reaction number 2. Something else we can notice, this term here doesn't show up anywhere else in the target or in the other reactions. So if we use the second equation, there's going to be no way to get rid of that term. And we don't want that term. And if we can't get rid of it if we use it, then we shouldn't be using it. The last thing to notice here, our sides are messed up a little bit. we have our rust on the left side of the equation. We want it on the right, so we are going to have to do some manipulating. So let's try reversing reaction 3. So we can get our rust on the right side, and then we can add it to reaction 1 and see what happens. So here we have reversed our reaction. And we also changed the sign on our delta H. Remember, if we reverse a reaction, we also need to change the sign on our delta H. And now we can see some common terms here. We have 4 aluminums on this side and 2 on this side. And so this stuff doesn't quite cancel. So maybe there's another way that we can get this to cancel. Maybe another manipulation that we can do to get these to cancel. So take a second now and think about it. So reaction 3, this one on the top here, if we times it by 2, then our 2 aluminums here is going to become 4 aluminums. And that's this guy here. And then it'll cancel with the other aluminums. So we do have to times everything by that. So let's check. We know it's going to work with this aluminum, but let's make sure it's right. So we took our reversed reaction and we multiplied it by 2. And when we do this, remember, we also need to times our delta H by 2. So our delta H here for the third reaction has been doubled. Now if we add them together, we can notice that both of these terms cancel. We can simplify that and we get our target equation for rust. Because we added these 2 reactions, we need to add the delta H's to find our target enthalpy of formation. So we add those up. And we get our answer here that rust has a delta H, or an enthalpy of formation, of negative 824.2 kilojoules per mole. So how did we get from negative 1,600 to negative 824.2? Remember that we were asked to find the molar enthalpy of formation for rust. And this second last line here was the enthalpy of formation for 2 moles. Remember, the coefficient in front of the term is the number of moles that we have. So we have 2 moles here, so we divide by 2. So here's a link to the first video. Please try the worksheet that will be in the description. The link will be in the description for that. Try the worksheet. If it's going well, finish it. If you're struggling, watch the first video again and work your way through. Hope everyone has a nice night. Take care.